Imagine for a moment your incredibly intelligent AI assistant,
Uh,
the one that can draft essays, write code, maybe even compose music. And then suddenly it makes this baffling, almost childlike mistake.
hmm.
Or maybe you've just heard about some groundbreaking new scientific discovery and you wish your AI could instantly integrate that fresh knowledge, learn from it, adapt without needing like a massive multi-million dollar software overhaul.
Right, it's like having this brilliant colleague who seems to have read every book in the world, yet sometimes just struggles to understand a simple new context.
Yeah.
Or maybe needs to go back to AI school every single time a new piece of information pops up.
Yeah.
Current large language models, LLMs, they're fascinating in their power, absolutely, but they often operate as this sophisticated yet kind of rigid black box.
Exactly. And that
Yeah.
rigidity, those baffling blind spots, and just the sheer computational effort it takes to teach them something truly new about our, rapidly evolving world, those are the core frustrations we're tackling today. Hey everyone, welcome to Computer Science Tech Paper Summary. I'm Alex.
And I'm Jordan, and today we're diving into a genuinely fascinating research paper that aims to, well, fundamentally change how we think about the brains of these powerful AI systems.
Okay, so the paper we're unpacking today is titled Decoupling Knowledge and Reasoning in Transformers, a Modular Architecture with Generalized Cross-Attention. It's from Xinyu Guo and Wenguang Chen, researchers from Tsinghua University and Ant Group. And this isn't just some incremental tweak.
No, not at all.
It's really a foundational rethinking. It's
Yeah.
tackling some of the biggest limitations of current LLMs. Their transparency, their ability to adapt to information that didn't even exist when they were first trained, and even how incredibly massive they need to be to show that impressive intelligence.
Hmm.
What they're really doing here is like laying the groundwork for AI that's not just powerful, but also way more understandable, agile, and capable of truly continuous learning.
Yeah, and if we kind of zoom out a bit, this work really touches upon a core philosophical question in AI, doesn't it? Like,
Yeah.
what is intelligence? Is it just about memorizing staggering amounts of data?
Hmm.
Or is it also about understanding how to use that data effectively? And, crucially, being able to dynamically update that knowledge as the world changes around it. This paper argues we basically need a completely different paradigm for how AI stores, accesses, and applies its knowledge. It's a pretty bold step toward maybe a more robust form of artificial intelligence.
Okay, so let's dig in. To really appreciate the solution this paper proposes, we first need to grapple with the fundamental challenge it's addressing. The inherent design of today's most powerful AIs, what the researchers call the monolithic AI brain. Can you help us visualize the core architecture of a standard transformer and tell us why calling it monolithic is such a problem?
Certainly. So, at its heart, the transformer architecture is basically the engine behind pretty much every large language model you interact with today, right? Whether it's a chatbot or one of those generative AI image systems. Imagine it as a single, incredibly dense, interconnected neural network where everything is just interwoven from the ground up. The paper's Figure 1A illustrates this quite well.
Hmm.
You see this single linear pipeline where data flows through a series of identical blocks.
Okay.
Each block typically contains two main components. First, there's a masked multi-head self-attention layer. This part is brilliant at understanding the context of each piece of information, say, a word, by seeing how it relates to every other word in the input sequence.
So it's kind of like a word figuring out its true meaning by looking at its immediate neighbors and maybe even distant relatives. In a sentence, like bank means one thing if it's next to river and something totally different if it's near money.
Precisely. That's exactly what self-attention excels at. And then the output from that sophisticated attention mechanism feeds into the second key component, something called a feed-forward network, or FFN. Now, these FFNs are really the central focus of this paper.
Ah.
Conceptually, an FFN is a relatively simple structure. It's typically just two linear transformations with a nonlinear activation function kind of sandwiched in between. It processes each token's representation independently, but crucially, it's still operating within this single, continuous, deeply connected pipeline.
Right.
So, going back to your analogy, if the attention layer figures out that bank means a financial institution in this context, the FFN then processes that specific interpretation further, integrating it with all the other contextual information it's received.
Okay.
The fundamental issue, the monolithic part, is that within this design, everything is essentially one giant interwoven system. There's no clear, explicit separation between what the model knows, its vast repository of facts, concepts, world knowledge, and how it thinks. its reasoning capabilities, how it processes and applies that knowledge. It's all mixed together.
That makes so much sense. It's like trying to understand how a master chef bakes a cake if the recipe, the ingredients, and the chef's actual baking skills are all just blended into one indistinguishable goo.
Yeah.
You can't tell if the cake is, undercooked because of a flawed recipe, or maybe stale ingredients, or just clumsy baking technique. Everything is just one massive, dense blob of learned parameters, those billions or even trillions of weights and biases that define the model. This is what the paper calls the deep entanglement of knowledge and reasoning, right? And that's the core challenge they're trying to unravel.
That's a perfect analogy, actually. The paper is careful to define knowledge as the factual information, the concepts, the linguistic rules, all the patterns the model has soaked up during its extensive training, essentially its understanding of the world. Reasoning, on the other hand, is the model's ability to process, apply, and generate new outputs based on that knowledge.
Yeah.
In current transformer architectures, these two absolutely critical functions are deeply, you could say, inextricably mixed within the model's parameters. And this entanglement means that if you want to understand why a model made a specific decision, or if you need to update just one particular piece of information, it becomes incredibly difficult to isolate that specific knowledge without potentially causing, unintended side effects across the entire model. It's like trying to change just one ingredient in that chef's cake batter without messing up the whole thing.
And this fundamental entanglement leads to some very specific and actually quite severe real-world limitations that we run into with LLMs today. Let's start with interpretability. Why is this such a huge barrier, especially when we talk about using AI in, high-stakes applications?
Oh, it's a massive roadblock. Because knowledge isn't stored in these clearly defined separate compartments, right? It's distributed across the entire network, especially within these feed-forward networks we mentioned. It's incredibly difficult, maybe even impossible sometimes, to pinpoint which specific piece of information or which learned fact within the model directly led to a particular prediction or output. Imagine an AI assisting in a medical diagnosis. It tells you a patient might have a certain rare condition. If it can't explicitly tell you why it arrived at that conclusion, or which specific symptoms and knowledge points it considered most relevant, how can a doctor or a patient possibly trust it?
Yeah, you absolutely need that audit trail.
Exactly. The paper gives a vivid example. They say the FFN for the word bank might encode both the concept of a financial institution and the site of a river, making it difficult to disambiguate in different contexts. This kind of distributed opaque encoding means that when an error happens, and they do happen, it's incredibly hard to trace the source of that error or to correct it precisely. This lack of transparency and accountability is just, unacceptable in critical fields like healthcare, legal reasoning, financial analysis, you name it. We desperately need to open up that black box.
Okay, so beyond just understanding why an AI says what it says, there's this equally pressing issue of adaptability. Integrating new knowledge like the latest breaking news or a newly published scientific discovery, or even just connecting these models to external live data systems that sounds incredibly inefficient and complex in the current setup. I know there are some attempts to bridge this gap, like retrieval augmented generation or RAGI. How does RAG try to solve this, and why isn't it, the ultimate solution?
Yeah, RAG is a really ingenious current approach that tries to give LLMs access to up-to-date external information. Conceptually, how it works is the LLM first performs a quick search, retrieving relevant documents or snippets from some external knowledge base, maybe a vast corporate database, a medical journal archive, or even just Wikipedia.
Okay.
It then takes that retrieved text and simply concatenates it, or you could say mashes it together, with the original input query from the user. The LLM then processes this combined, much longer text to generate its answer. It's essentially giving the AI a real-time Google search before it tries to answer your question.
Which, on the surface, sounds like a perfect solution, right? More context should always be better.
It sounds ideal, yeah, but it comes with some significant limitations that stop it from being a truly seamless, scalable solution. Firstly, there's what the paper calls context dilution. Imagine you've asked your AI, what are the latest breakthroughs in fusion energy? And RAG, trying to be helpful, retrieves several lengthy scientific papers, a few news articles, maybe some historical context, and then pastes all of that right next to your very specific question. The model now has to wade through all that additional, sometimes kind of tangential context just to find the precise answer to your specific query.
Ah, right. It's like handing a student an entire library and saying the answer's in there somewhere. Along with 100 other topics, the signal gets lost in the noise.
Exactly. The model has to work significantly harder to separate the factual knowledge from the user's specific question. So the efficiency gains you might hope for get eaten up by the need to filter.
Secondly, RA typically performs a single initial retrieval. The knowledge is pulled only once, right at the very beginning of the entire processing chain, before the LLM even starts its internal reasoning steps.
Mm.
So if the model realizes, say, halfway through generating an answer that it needs more specific information or maybe a different angle on the topic, it can't just go back and retrieve it. It's stuck with whatever it initially pulled.
That sounds incredibly limiting, especially for complex reasoning tasks that might need iterative information gathering, like cooking a complex meal but only being allowed to check your ingredients once at the start.
It really is. If you miss something, too bad. And thirdly, current LLMs have a limited input window. They can only process a finite amount of text at once. If the retrieved info from RAG is too long, it gets cut off, meaning potentially crucial facts are lost. If it's too short, it's not enough to answer properly.
And without array, updating the core model is even worse. Well, yeah. Without RAG, incorporating new information into these monolithic models is even more problematic. It often requires significant resources and risking disruption to existing knowledge. Imagine having to retrain an entire model from scratch, which can cost tens of millions of dollars and take weeks or months of compute time just to update it on yesterday's news or a new scientific paper. It's simply not practical for real-world continuous learning.
Which brings us neatly to the third massive limitation, scalability. When you talk about parameter explosion, what does that actually mean for how these monolithic models grow, and why does it hinder progress towards truly comprehensive, knowledge-driven AI?
Right. Parameter explosion basically refers to the exponential growth in the number of learnable parameters, those weights and biases, within these massive models. Because knowledge and reasoning are so tightly coupled in current transformers, increasing one's capacity, like adding more facts or broadening the model's understanding, it disproportionately increases the other's capacity too. The parameters needed for reasoning also explode.
So it's like, to learn a new recipe, you have to completely rebuild your entire kitchen from scratch, making it bigger and bigger with every new dish you master.
That's a great way to put it, yeah.
Yeah.
And the more dishes you learn, the bigger the kitchen, the more expensive and unwieldy it gets to build and maintain. That's the parameter explosion hindering progress. It's a stark contrast to how human cognition works, isn't it?
Totally. We can learn a new fact without having to completely relearn how to learn.
Absolutely.
Hmm.
Humans can efficiently transfer existing reasoning capabilities to new knowledge. We learn a new historical date, a new name, a new scientific principle without needing to relearn how to read or combine concepts or infer meaning or speak. We just integrate that new fact into our existing cognitive framework.
Yeah.
LLMs, as they are now, they just can't do this easily. Fine-tuning helps a bit. It's less costly than full retraining, but it still suffers from this thing called catastrophic forgetting.
Catastrophic forgetting. That sounds bad.
It is. It's a phenomenon where when you train a model on new information, it tends to forget old, previously learned, and sometimes completely unrelated information. It's like teaching a student about World War II, and suddenly they forget how to do basic arithmetic.
Wow. So you fix one thing and inadvertently break something else. And I guess there are diminishing returns, too. Just making the model bigger doesn't always help proportionately.
Exactly. After a certain point, simply making the model bigger or fine-tuning it more doesn't lead to proportionate gains in performance. It becomes an incredibly inefficient way to scale knowledge and intelligence.
Okay, so given all these problems, the lack of interpretability, the adaptability struggles, the massive scalability challenges, it's super clear there's a desperate need for a smarter, more efficient way for AI to learn and process knowledge. You mentioned some prior research suggesting FFNs might act like key value memories.
Yes, that was an insightful line of research by Java and others. It was a significant conceptual leap, recognizing that FFNs might be implicitly storing information like a hidden database. But interestingly, this insight actually created a new problem for researchers.
Ah, okay, what was the new challenge then?
Well, this raises an important question. How do you take that really fascinating insight that FFNs might be implicitly storing knowledge like a memory bank and actually turn it into something explicit and practically useful? The new challenge for the field became, How do you design an AI system where knowledge is both globally consistent, so all parts of the model access the same fundamental truths?
Right, no contradictions.
Exactly. While also allowing for highly contextualized layer-specific access. Imagine trying to build a multi-story library that's universally accessible to everyone in the building, but also somehow ensures that each person, depending on what floor they're on and what specific task they're doing, gets exactly the right section of the library presented to them automatically, without them having to search through the whole collection.
Hmm, that's a tricky balance. Global access, but personalized views.
Precisely. Current approaches really struggle to reconcile these two seemingly competing demands: global consistency and context-specific retrieval.
Okay, so the core goal of this particular research, then, is to address exactly that gap. They're proposing a novel modular transformer architecture. The aim, as they put it, is to enable seamless interaction with external knowledge bases, facilitating continuous learning, knowledge sharing, and independent scaling of knowledge capacity. It sounds like they want to make the AI's knowledge base truly plug-and-play, dynamic, external.
That's the vision, yes.
And a really crucial contribution of this work, beyond just proposing a new architecture, is this rigorous theoretical analysis they did. They present a formal argument showing that the standard feed-forward network within a transformer can actually be expressed as a specialized case. They call it a closure of their generalized cross-attention mechanism. Now, here's where it gets really interesting for me.
Yeah, this is the core theoretical insight.
It feels like a monumental revelation because it reveals this hidden implicit knowledge retrieval role that FFNs have been playing all along. It doesn't just theorize, it proves that their proposed modular system isn't just a neat new idea. It actually describes what current transformers are already doing, but in a much more explicit, transparent, and ultimately more manageable way.
Mm-hmm.
This mathematical proof, showing functional equivalence, especially when the knowledge base is trained within the model, gives such a solid theoretical foundation for exploring external knowledge later. It's like finding the hidden user manual for a complex machine you thought you understood, and suddenly realizing its true underlying mechanism. It validates their whole approach.
Absolutely. It connects the known with the proposed in a very rigorous way.
Okay, that's a profound shift in perspective. So let's get into the nitty-gritty. How does this modular design actually work? The conceptual shift is from that single monolithic brain we talked about to what you described as a brain with a dedicated, accessible knowledge library, like in Figure 1B in the paper. What are the two core requirements for building an explicit knowledge base like that? One that would make it truly effective and better than what we have now.
Right. If you want to move from an implicit baked-in knowledge system to a separate, explicit, and truly usable knowledge base, it really needs two critical characteristics to function efficiently and scale effectively. First, it needs global sharing.
Global sharing.
Meaning the knowledge base itself is shared across all parts of the model. This is absolutely paramount for parameter efficiency. If every single layer of the transformer had to carry its own duplicated copy of the entire knowledge base, you'd face massive redundancy, leading to an even worse parameter explosion than we see now.
Right, like duplicating the entire library for every single room in a huge building. Wildly inefficient.
Exactly. A shared knowledge base also inherently promotes knowledge consistency. You absolutely don't want different parts of the model operating on contradictory facts or, say, outdated information.
Makes sense.
And finally, it significantly facilitates efficient management. Updating one central knowledge base is far simpler and more robust than trying to update multiple distributed ones. This is vital for continuous learning and adapting quickly to new information.
Okay, so global sharing is key for efficiency and consistency. You don't need to duplicate the entire internet for every brain region. But then how does that work with the second requirement you mentioned, layer-specific views? If the knowledge is globally shared, how do different layers access just the part they need, tailored precisely to their current processing task and their level of abstraction?
This is where the elegance of their design really comes through. Different layers of a transformer, they're designed to process information at different levels of abstraction, right? The early layers might be extracting very low-level features, maybe understanding grammatical structure or identifying basic semantic links. Deeper layers, though, are typically involved in much more complex stuff, like understanding nuanced semantic relationships, doing multi-step logical reasoning, or generating highly creative text.
Okay.
So each of these layers needs to access a specific view of the knowledge base that is precisely relevant to its unique context and its current computational state.
Got it. It's like how different parts of your brain process the same sensory input. Your visual cortex sees shapes and lines, while your language center interprets meaning if those shapes are words. They're looking at the same underlying info, but from different specialized perspectives, pulling out different insights.
Exactly that. And their proposed modular architecture cleverly achieves this by introducing a globally shared knowledge base E. You can think of E as this vast central matrix, like a digital library, where each row represents a distinct knowledge entry. This E is designed to be shared across all layers of the transformer.
Okay, shared library.
But the crucial innovation is how it's accessed. It's accessed via dedicated cross-attention mechanisms, embedded within each layer. This mechanism explicitly separates the knowledge itself, which lives in E, from the specific reasoning process happening within each layer.
So the magic is really in how each layer interrogates or looks at this shared knowledge base. It's not just reading the whole thing.
Precisely. Each attention head within these modular blocks isn't just passively observing. Instead, it actively learns distinct projection matrices. You can think of them as specialized lenses or filters for its queries, keys, and values. And crucially, these lenses are unique for each layer.
Ah, layer-specific lenses.
Exactly. That's the layer-specific transformation. These unique lenses allow each layer, dynamically and on the fly, to focus on different aspects of information within the globally shared knowledge base, E, based entirely on that layer's current processing context. It ensures that while the knowledge is universal, its retrieval is highly contextualized.
Okay, can you walk us through that simplified process a bit more? How does a specific layer actually interact with the shared knowledge base to pull out the info it needs?
Sure. So imagine the current layer has processed some information, and its current internal state is like a thought or a query it's
Right.
formulating. This internal query gets transformed through a specific projection matrix unique to that layer to become the actual query used for knowledge retrieval.
Okay, it formulates a question.
Right. Now, the globally shared knowledge base, E, also has its entries transformed through its own set of rejection matrices to become keys and values. Think of the keys as the searchable index of the library and the values as the actual content of the books.
Index and content. Got it.
The paper then introduces this novel function called generalized attention. This function takes the layer's unique query, compares it against all the keys in the knowledge base, identifies the most relevant ones based on that comparison,
Finds the right books.
and then pulls out the corresponding values, the actual pieces of knowledge, the content of those books. This retrieved and processed knowledge is then seamlessly integrated back into the layer's ongoing computation, contributing directly to its output. It's a much cleaner, more explicit, and ultimately more transparent way for the model to access and use information from a separate, dedicated knowledge source.
Wow. Okay, so this modular design, even if the knowledge base E is initially trained jointly within the model, so it's still internal for now, it seems like it offers some really significant advantages for the future. What are those immediate and maybe long-term benefits?
Even in this initial jointly trained setup, the conceptual leap itself is powerful. Firstly, you get explicit knowledge representation. Knowledge is no longer scattered and implicitly encoded throughout the entire network. It's now explicitly stored in a separate, accessible module E.
Right.
This provides a vastly clearer conceptual framework for understanding exactly what information is being used for a given prediction or decision. You can literally point to E and say, that's the knowledge the model is drawing from.
Which means it's not buried deep within those complex interwoven weights of a monolithic model. Makes it much easier to inspect and maybe even understand.
Exactly. Secondly, this architecture lays the foundation for dynamic in-context knowledge retrieval. Unlike current RX systems, remember, where knowledge is retrieved only once at the very beginning.
Yeah, the single-shot retrieval.
Right. This mechanism allows for knowledge retrieval at each and every layer of processing. The model can ask for new information, refine its search, or access different facts as its internal thought process evolves and its context shifts.
Whoa, hold on. So it's like the model is constantly referencing its library as it processes information, not just at the very beginning of a complex thought, but at every single step of that thought. That sounds like a huge difference.
It is a fundamental difference. Precisely. Thirdly, it's a profound foundation for independent knowledge-based management. Looking ahead in future work, if you need to update E, maybe adding new facts, correcting existing ones, even pruning outdated info, it won't necessarily require retraining the entire model's reasoning capabilities, which live in those projection matrices and the self-attention parts.
Wow.
That's a massive leap in adaptability and cost efficiency. It means you could potentially update your AI's understanding of the world without spending millions of dollars and weeks of compute time.
That's the dream, isn't it? And finally, I guess, a true foundation for independent scaling.
Exactly.
Hmm.
This lays the groundwork for scaling the model's knowledge capacity independently of its reasoning capacity. You can grow your digital library of facts and concepts without having to rebuild or disproportionately expand the entire architecture of the brain itself. Imagine expanding a library's collection without needing to build entirely new wings or floors for the building's central admin offices.
Okay, this sounds incredibly promising, especially for future AI systems that really need to constantly adapt. But how does this generalized cross-attention actually work to retrieve knowledge? You mentioned it goes beyond standard attention. What's the fundamental difference in how it selects the information?
Right. So traditional attention mechanisms, like the self-attention commonly used within transformers, typically employ a softmax function on the calculated query key similarity scores.
Softmax, okay.
The problem with softmax when you're trying to do selective knowledge retrieval is that it assigns non-zero weights to all knowledge entries in the database, even if they're only, remotely relevant.
Ah.
This means the model is always trying to pay a little bit of attention to everything, which is really suboptimal when you want to pinpoint and pull out only the most crucial, relevant pieces of information. You need a way to filter and transform much more precisely to really focus in.
So softmax is like shining this diffuse soft light on every single book in the library, giving everything a tiny bit of attention, even if you just need one specific fact. You want something that says, no, I only care about these specific books and I'll ignore all the others completely. Like a spotlight.
Exactly. A spotlight is a good analogy. That brings us to phase one, selective retrieval with sparse activation. Instead of softmax, they replace it with ReLU, which stands for rectified linear unit, applied directly to that query key similarity matrix.
ReLU. Okay. How does that help?
What's truly fascinating here is how ReLU acts as this sharp, decisive filter. Unlike softmax, which spreads attention thinly, ReLU basically says, if the relevant score for a piece of knowledge isn't above 0, I ignore it completely, setting its weight to 0.
Oh, interesting. Just cuts it off.
It creates sparsity. That means the mechanism focuses only on the truly relevant information, effectively filtering out anything not immediately useful. If a knowledge entry isn't helpful, boom, it receives 0 attention.
That sounds much more efficient and targeted for search and retrieval. But then there's phase two, knowledge-specific thresholding, which they call the IF condition. What does that add to the process? Is 0 not selective enough?
Well, while ReLU introduces sparsity by setting that uniform threshold of 0 for all knowledge entries, the paper argues that, realistically, different entries have varying levels of inherent relevance or ease of access. Some facts might be more easily retrieved, perhaps. Others might require a higher degree of similarity or some specific condition to be met before they're even considered relevant.
Ah, okay.
To account for this, they introduce a knowledge-specific thresholding function. They implement this with a small neural network called an MLP, a multi-layer perceptron. This function generates a unique, learned threshold that is added to the query key similarity score before the ReLU filter is applied.
So what does this all mean then? It's like having a smart, dynamic filter that understands not all knowledge is equally easy to access or equally important in every single context. Some facts might have a higher barrier to entry, a specific if condition they need to meet before they're even considered relevant by the model.
Precisely. It allows for a much more nuanced and intelligent determination of relevance than just a simple 0 threshold. It gives more granular, adaptive control over which knowledge is deemed relevant based on its inherent characteristics and the layer's specific needs, not just its raw similarity to the query.
Okay, that makes sense. And then there's phase three, transformation bias for semantic bridging. After all that selecting and weighting, they add another component called a transformation bias, specific to each layer. This raises an important question. Why is this bias important? Why do we need yet another adjustment after all that sophisticated filtering and selection?
It's actually crucial because of the fundamental difference in how information is flowing here. Remember, unlike self-attention, where the query and value information comes from the same place, they're both internal representations of the input sequence here. In cross-attention, we're connecting a layer's internal representation with a completely separate knowledge base, E.
Right, different sources.
The current layer's processing context and the external knowledge entries, they're initially in distinct semantic spaces. They speak slightly different languages. This transformation bias helps bridge that semantic gap. It ensures the retrieved knowledge isn't just pulled out, but also properly transformed and aligned into a format that seamlessly integrates with the current context and internal representation of the model's processing.
Ah, so it translates the retrieved knowledge into the layer's native language so it can actually use it properly.
Exactly. It makes the retrieved information understandable and directly usable by the current layer, allowing for smooth assimilation of external facts into the ongoing reasoning process. Without it, the knowledge might be retrieved, but maybe not properly assimilated or understood in context.
Okay, so that's how the modular design works and how the generalized cross-attention helps retrieve and integrate relevant knowledge. Now, for the big reveal, the central theoretical contribution of this paper, which you hinted at earlier, this is where it gets really interesting for me. They claim that the feed-forward network, the FFN, which has always been this somewhat mysterious but essential component in every standard transformer block, they claim it can now be interpreted as a specialized, kind of collapsed case of their generalized cross-attention mechanism,
Yes.
which means formally that the FFN function in a layer is basically equivalent to their cross-attention mechanism querying some kind of implicit E knowledge base. What does this profound finding mean for our understanding of current LLMs, like in plain language?
This paper, it essentially peels back the curtain on one of the most opaque parts of current LLMs. It shows that those seemingly arbitrary FFNs aren't just performing some general nonlinear mathematical transformation,
Yeah.
which is kind of how we might have simplistically thought about them.
Yeah.
They're actually performing a hidden miniature version of knowledge retrieval from a knowledge base that has been baked in to their very structure during that initial massive pre-training phase.
Whoa. So FFNs were essentially doing exactly what their proposed modular architecture is doing explicitly, but they were doing it implicitly, hidden inside, without anyone truly realizing it.
Exactly. They referred to this hidden embedded knowledge base as implicit E. You can understand this implicit E as a highly compressed representation of knowledge, a vast collection of facts, patterns, concepts, learned and deeply encoded within the complex weights of the FFNs during the model's initial, multi-trillion token pre-training. This clarifies that FFNs implicitly perform a context-dependent knowledge retrieval from this built-in unchangeable knowledge base. This connection provides a powerful theoretical justification for why FSNs exist and what they do, and it fundamentally validates the design of their generalized cross-attention. It also provides a formal basis for that key-value memory interpretation of FFNs, which was previously more of a hypothesis.
It's like discovering that a complex gear in an engine, which you thought was just for general power transmission, was actually a highly specialized, hidden micro-library indexing system all along. That's amazing.
It is a really neat insight.
And the paper even provides a simplified mathematical derivation showing how the complex generalized cross-attention equation kind of collapses or simplifies into the standard FFN formula when this implicit E is static or folded into the weights. Can you explain this folding idea a bit? Sounds quite elegant.
It is quite elegant. So the standard FFN has its own set of learnable weights and biases, right? Often denoted as W1, B1, W2, B2 for its two linear layers. The paper demonstrates that when the knowledge base, E, within their generalized cross-attention framework, is static, meaning it's not dynamically changing during the process, as it wouldn't be inside a pre-trained FFN, you can mathematically pre-compute and combine certain terms.
Okay.
For instance, the transformations of the knowledge base E into keys and values using those projection matrices, WLK, WLV, they become fixed matrices because E itself is fixed. Similarly, that knowledge-specific thresholding function we talked about, B1LE, it also collapses into a fixed bias term because it only depends on the static E.
So these fixed pre-computed values derived from a static knowledge base, they are essentially the folded implicit E. They represent the knowledge that has been compressed and absorbed into the FFN's very structure.
That's the essence of it, yes. And when you substitute these folded terms back into the full generalized cross-attention equation, the mathematics beautifully show that it becomes the standard FFN formula. Right, LU, HL, W1 plus B1, W2 plus B2.
Oh.
This mathematically proven equivalence means that their modular architecture, when its knowledge base E is trained within the model in this static way, is functionally identical to a standard transformer.
Yeah.
So you'd expect identical performance under this specific joint training regime.
Okay.
It's a really powerful validation of their design. It essentially says, look, we've created this new explicit way of building this, but we can prove that if you make our knowledge base static and internal, it behaves exactly like the FFNs you already have, thereby revealing the hidden function of those existing components.
This is truly groundbreaking stuff. It feels like a moment where a long-standing black box in AI suddenly becomes a little bit more transparent, maybe even understandable. What are the broader implications of this equivalence for the field?
Well, first and foremost, it provides a crucial theoretical justification and a powerful new interpretation of FFNs. They're no longer just these arbitrary nonlinear transformations. They are revealed to perform a specific form of context-dependent knowledge retrieval, complete with knowledge-specific thresholding and transformation bias. This makes FFNs far more interpretable. We now have a conceptual framework for understanding what they're actually doing inside the model.
It's like finding out the seemingly random squiggles on a complex circuit board are actually a tiny self-contained search engine constantly pulling specific data. And this revelation, it also explains a lot about why these models are just so massive, right? They're huge parameter requirements.
Precisely. The implicit encoding of E within the closure FFN directly explains why transformers need such substantial parameter requirements. They're literally storing vast amounts of compressed knowledge, that implicit E, directly within their FFN weights. Our modular architecture, by proposing to externalize the knowledge base in future work, offers a potential solution to this, allowing for hopefully more efficient and independent scaling of knowledge capacity. Instead of adding more and more parameters to the model itself, you could maybe just add more entries to its external knowledge base.
And that idea of layer-specific views, does that apply to standard FFNs too, now that we know this? Even though we thought the knowledge was just generally intertwined.
Yes. Interestingly, the derivation reveals this subtle but important point. Because the folding process that leads to the FFN involves layer-specific projection matrices, WLQ, and biases, B2L. It implies that each layer in a standard transformer effectively accesses a different view of the same implicitly encoded shared knowledge.
Huh.
So even within that monolithic black box, different parts of the AI brain are looking at the same underlying knowledge, but from their own unique, specialized perspectives, selecting and transforming it differently to serve their immediate computational needs. It's truly a complex dance, even when it's hidden from view like that.
Okay, this is truly fascinating work. It offers a profound new understanding of how current LLMs operate and a really clear path forward. But, as with all cutting-edge research, there are inherent limitations in areas that maybe warrant some critical reflection. The paper explicitly states its current focus. Can you elaborate on that and maybe explain why it's more of a theoretical rather than an immediate empirical breakthrough at this stage?
Indeed. The paper primarily focuses on establishing the theoretical framework and demonstrating that mathematical equivalence for the specific case where the shared knowledge base E is trained jointly within the model.
Okay, the internal knowledge base case.
Right. This means that for this specific initial setup, the immediate empirical
So it's more like a proof of concept of how a decoupled system could work, proving the blueprint is sound, rather than an immediate ready-to-deploy system that dramatically outperforms everything else today. What's the why behind focusing on the theory first, then? Why not just jump straight to the empirical results showing off the benefits?
That's a great question. And it really speaks to the nature of foundational research like this. The true transformative benefits of this modular design, things like enhanced interpretability, vastly improved adaptability, truly independent scalability, these are long-term goals.
Right.
And they absolutely require significant further empirical work, specifically with external pluggable knowledge bases. This paper is essentially laying the indispensable theoretical groundwork, establishing the very possibility and the soundness of this decoupled approach. You can't just take an external knowledge base and arbitrarily try to hook it up to a transformer and expect it to work seamlessly without first fundamentally understanding how its internal knowledge system actually functions.
Okay, you need to understand the original before you can replace a part.
Exactly. This theoretical derivation provides that crucial understanding. They are essentially saying, look, we've meticulously shown the blueprint for how we can decouple knowledge and reasoning, and we've rigorously proven it's consistent with existing models, even revealing their hidden mechanisms. Now, the next ambitious step is to actually build and rigorously test the externalized system. It's a very strategic move, building the theoretical fortress before launching the big empirical expedition, so to speak.
And they even provide a really helpful comparison in Table 1, meticulously outlining the trade-offs between the monolithic end-to-end and decoupled modular architectures. Let's walk through a few of those because they really highlight the strategic thinking here. For instance, performance. Monolithic models offer high direct optimization because everything is baked in. But what about the decoupled ones?
Right, as we just discussed, they're theoretically equivalent under joint training when that knowledge base is still internal. But the paper acknowledges, with truly external knowledge bases, performance could potentially be lower, at least initially, if the knowledge representation, the retrieval mechanisms, and the integration aren't perfectly optimized yet. This is an acknowledged potential trade-off they seem willing to accept in the short term for the larger long-term benefits they envision.
Okay.
It's about prioritizing this fundamental architectural innovation for future gains over maybe immediate marginal performance improvements today.
Which includes dramatically enhanced interpretability for the modular system, right? That's a core problem they're trying to solve compared to the very limited interpretability of monolithic models.
Hmm.
And adaptability, which we touched on earlier, that seems like a huge win for modularity.
Absolutely. Monolithic models have inherently low adaptability because adding significant new knowledge often requires that expensive, time-consuming retraining or fine-tuning, which, remember, can lead to catastrophic forgetting.
Yeah.
Modular systems, with their separate, potentially pluggable knowledge bases, promise high adaptability. Through modular updates, you could potentially update just the knowledge base without having to touch or retrain the core reasoning network at all.
That sounds like a complete game changer for continuous learning in real-world AI applications. What about scalability? How do they compare there?
Monolithic models are fundamentally limited because of their entangled growth, where knowledge capacity and reasoning capabilities are just inextricably linked within the same giant set of parameters. This leads straight to that parameter explosion we discussed. Modular systems, in stark contrast, offer the promise of enhanced independent scaling. You could potentially grow your knowledge base, adding more facts, more concepts, without having to disproportionately grow your reasoning network, potentially saving immense computational resources down the line.
But there's a potential downside they acknowledge regarding inference efficiency, right? Monolithic models are often fast at inference because everything is pre-computed and baked in, but modular ones could be slower.
Potentially slower? Yes, that's a fair point they raise. It's due to the added computational cost of actively retrieving information from that external knowledge base during inference. Every time the model needs a fact, it has to perform a lookup operation. This is a significant practical engineering challenge that future work will absolutely need to optimize. It's not necessarily a showstopper, but it's definitely a known hurdle to overcome.
Okay. And finally, on knowledge representation itself.
Monolithic systems inherently rely on implicit distributed knowledge spread opaquely throughout their parameters. Modular systems, however, aim for explicit centralized knowledge stored in a dedicated knowledge base. This inherently makes the knowledge directly inspectable, auditable, and manageable.
So the paper clearly lays out these trade-offs. The authors are pretty direct in arguing that the potential benefits of decoupling knowledge in reasoning, things like interpretability, adaptability, independent scaling, and richer, more transparent interaction with external systems, they believe these outweigh this potential trade-off in inference speed, especially when considering the long-term vision of robust, evolving AI. They're definitely playing the long game here, prioritizing a fundamentally better architecture for the future.
Exactly. They believe the long-term gains in building more human-like, continuously learning, and transparent AI systems far justify the initial complexities and potential performance nuances that might arise during the transition to truly externalized knowledge bases. It's really an investment in the future architecture of AI.
Okay, so this foundational theoretical work is truly a springboard for future exploration of external, pluggable knowledge bases and associated empirical evaluations. It's about moving beyond an implicit, baked-in knowledge base to a real, accessible, and dynamic one. What are the key research directions they outline for this ambitious future work? What are the next big challenges to actually tackle to make this vision a reality?
They highlight several really crucial and exciting areas that need serious work to realize the full potential of this architecture. First, there's external knowledge base implementation and management. This involves some significant practical challenges. For instance, how do you jointly train the main LLM with a dedicated KB embedding model? This separate model will be responsible for generating those high-quality, searchable knowledge base embeddings, allowing the LLM to retrieve relevant entries effectively.
So it's about optimizing the compatibility between the query the LLM asks and the knowledge representation in the base, making sure the library index is perfectly aligned with the reader's questions.
Precisely. You need the knowledge base itself to be AI-friendly, structured in a way the LLM can query effectively. And second, once you have these knowledge base embeddings, how do you efficiently store and manage them? This is a non-trivial data engineering challenge.
Yeah, I bet.
It includes everything from how to maybe re-embed knowledge when new information comes in, how to efficiently insert brand new facts, or even how to delete outdated ones during inference, that is, while the model is actively trying to answer a question in real time. This is crucial for a truly dynamic, living library that can keep up with rapidly changing information, like financial markets or breaking news.
That's a massive challenge, especially for rapidly changing info. Imagine trying to constantly update a global encyclopedia in real time, instantly reflecting every new piece of information the moment it happens. That's intense.
It is. And third, they raise the critical question of knowledge representation and structure. Currently, they conceptually consider knowledge as these individual discrete entries in E. But, as we've discussed, FFNs implicitly encode knowledge in incredibly complex, high-dimensional, and often distributed ways. So how should you represent knowledge effectively in these external KBs? Should it be simple atomic entries or maybe more complex, structured, high-dimensional representations that better mimic how FFNs implicitly encode information? That decision will impact everything from retrieval accuracy to storage efficiency and management complexity. It's a big design choice.
Okay, and next they revisit scaling and efficiency, diving deeper into the computational and memory trade-offs again. For listeners who might be, intimidated by academic notation, can you break down the numbers and explain the ultimate goal for efficiency here? What's the hope?
Absolutely. The paper reiterates the current computational burden of standard FFNs. While we don't need the exact formulas here, the key takeaway is that these operations scale significantly with the length of the input text and the model's internal size. This could be substantial for very large models. Now, a naive implementation of their generalized cross-attention mechanism, querying a full external knowledge base, meaning literally scanning every single piece of knowledge for every query, that would be even more expensive computationally, especially if the number of knowledge entries E is absolutely enormous, like billions or trillions.
Okay, yeah, that sounds like it would be much, much slower than even the current monolithic models. That would potentially defeat the whole purpose, right?
It absolutely would. But the crucial point and their ultimate goal for future efficiency lies in what they call cross-attention with folding and retrieval to just a subset of the knowledge base. The core idea here is that you don't query the entire knowledge base every single time.
Ah, smart retrieval.
Instead, the model intelligently retrieves only a small, highly relevant subset of knowledge entries from the massive knowledge base. If this subset, maybe just a few hundred or 1,000 highly relevant entries out of millions or billions, is much, much smaller than the total size of the knowledge base, then this intelligent retrieval mechanism has the potential to offer substantial computational savings, even when you factor in the added cost of performing that retrieval operation.
Okay.
The ultimate goal is to optimize for highly efficient and truly scalable knowledge-driven LLMs by being smart about what knowledge you access when.
So what does this all mean for the future of AI then? It means instead of needing to train a brand new, colossal, and increasingly expensive brain every time you want your AI to learn something new or access updated information, you might just update its external library card or add a new volume to its central knowledge repository. That sounds incredible for continuous adaptive learning.
That's the vision. And it's also critically important to note, again, that in their proposed architecture, unlike the unshared FFN weights in standard transformers that implicitly encode knowledge in that distributed way, the knowledge base E is explicitly shared across all layers.
Right, the global sharing.
That global sharing fundamentally reinforces the need for efficient knowledge representation to minimize the size of E and make externalization computationally feasible. And it's fundamental to achieving both parameter efficiency and knowledge consistency across the entire model. This research really feels like a pivotal step.
Absolutely. This paper fundamentally redefines our understanding of how transformer FFNs work, revealing them not just as abstract math functions, but as implicit knowledge retrievers. And maybe most importantly, it proposes a clear, modular path towards building AI systems with explicit, external, and dynamically updatable knowledge bases.
It's a really profound shift, potentially, from monolithic, opaque intelligence to a system that could be more transparent, adaptable, and continuously learning. It's about building AI that can not only tell you the answer, but potentially show its work, pulling from an identifiable, auditable, and continuously updated knowledge source.
So as you go about your day, think about this. Imagine an AI that not only tells you the answer to a complex question, but can also transparently show you the specific page or fact from its knowledge base that led to that answer, and maybe even explain why that particular fact was relevant to its reasoning process. What kind of trust, accountability, and entirely new capabilities would that unlock in fields ranging from scientific discovery to just everyday life? It's a glimpse into a future where AI isn't just a black box of impressive calculations, but maybe a transparent, adaptable, and continuously learning partner, truly mimicking some of the best aspects of human intelligence.